Okay, welcome back. Chapter 16, Sound and Hearing. We have a lot to cover in this chapter. We're going to, again, talk about sound waves in terms of longitudinal waves, kind of building upon what we did last time. We'll talk about how sound can propagate and how sound is going to propagate differently with different speeds in different materials. We'll talk about intensity levels and sound intensity levels. And then we'll start to look at musical instruments, open pipes, organs, flutes, and look at how pressure changes inside of these and how that affects the sound waves. We'll essentially make sound waves overlap and talk about what happens when they're one at the same frequency and two at different frequencies. And lastly, we'll look at the Doppler effect and how speed can affect the sound of the wave that you're hearing. Just some general thoughts to think about. How do we actually perceive sound? What is sound? What is the difference between music and noise? And we'll talk about how we can define a sound wave as either being the displacement of particles or pressure variations. And lastly, why do you hear a different frequency when a fire engine is coming towards you or going away from you? So we really defined sound waves last time as being a longitudinal wave going through a medium, and we thought about it kind of schematically over here, where we have particles that are moving back and forth, transmitting a wave. The wave is propagating in that direction for the way that I have it drawn here, and this particle is going to vibrate back and forth, in the case of this plunger, driven by that plunger. And we're going to have pressure nodes and antinodes that are going to propagate down the tube, and one wavelength is going to be the distance between one pressure node and the next pressure node, or we could think of it as one pressure antinode to one pressure antinode. The frequency with which we can hear is actually a huge dynamic range, ranging from 20 hertz to 20 megahertz, so 10 to the 6. The difference is going to be 10 to the 5th in terms of what we can hear. Ultrasonic sound waves are going to be sound waves that are above this 20,000 hertz, so the sound waves that dogs can hear in, for example. And infrasonic are going to be sound waves that are below our threshold of hearing, so below 20 hertz. And again, this figure to the right just kind of shows schematically a longitudinal pressure wave going through a medium. We can look at sound waves either by looking at the displacement versus position, shown here at the top, or we can look at it as the pressure versus position. Really, they're more or less the same thing. One thing to kind of think about is if we look at this as the displacement versus position for particles. So here we have a particle and it's moving back and forth, it's being pushed or pulled back and forth, where we have regions where the displacement is at a maximum, say here, 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 or a minimum, and here we're going to have minima in terms of our pressure here, 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 and here. So let me just kind of talk through that just a little bit more qualitatively. If we look at this region right here, we're going to here have particles that are being pushed to the right. So kind of in the cartoon here where we have some undisplaced particles, where y is greater than 0, these particles are being pushed to the right. When we look at having displacements less than 0, these particles are being pulled to the left. What that really means in terms of pressure is how densely packed are these particles crammed in there. And where y is going to be equal to 0, we're going to have the most particles crammed into the smallest amount of space, and we're going to have maxima in terms of pressure. Now, if you ask yourself, well, what happens at the next node in terms of displacement? So now we're looking at this point right here. Here we have particles that are being displaced to the left, and then over here we're going to have particles that are being displaced to the right, and so we're going to essentially have very few particles. We're going to reach our minima in terms of pressure, and so on and so forth as we work our way down through different positions. Now, how we actually perceive sound is we're going to say we have these pressure waves coming into the auditory canal, they're going to vibrate this membrane. What that membrane is called our eardrum. That eardrum is going to cause vibrations through these 3 bones in the middle ear, which then transfer the wave into the cochlea, which is filled with fluid. So we're going to have the sound wave now in fluid, and it's going to oscillate these little hair-like follicles inside of the inner ear. They're going to then vibrate back and forth, which translates these frequencies from a mechanical wave into an electrical signal that travels down the auditory nerve. So that's kind of a physicist version of how we hear sound. Now let's talk about our perception of what we're hearing. It turns out the harmonic content, or how many frequencies we're hearing, is going to affect our perception of sound. If we look first at, say, the pressure fluctuations that's going to reach your eardrum from, say, a recorder, the pressure variations is going to be a nice, fairly sinusoidal looking graph right here. And we could relate the amplitude of this guy to the loudness that we're hearing. The pressure variations that are very large are going to be very loud. It's very small, it's not going to be very loud. The frequency that we're hearing, in the music world, we would call that pitch. I say we, but really I can't really hear this type of stuff very well. If we look at the harmonic content, or how many frequencies we have, and we kind of look at the the probability of having these frequencies, this is a nice sinusoidal looking curve, and so we're going to have mostly one frequency and then a couple of overtones here. If we contrast that to, say, something very reedy, or like a reed instrument, we could now start to talk about objects that have more than one fundamental frequency, kind of talking about the timbre of an instrument. Now you can look at the pressure fluctuation coming off of a clarinet, and you can see it is going to be repeating itself. You can see the same type of behavior right there, and you could say in your mind that this is going to be roughly sinusoidal, but there's a lot of different frequencies mixed into this particular pressure wave right here. If you again look at the frequencies versus the probability or number of frequencies, there's going to be a lot of different harmonics that are added in right here, and really that's going to affect our perception of sound. If we consider the extreme case of white noise, then there's going to be roughly an equal amount of waves coming in at 20 hertz, 30 hertz, all the way up to 20,000 hertz. So white noise would be having equal number of frequencies of all the frequencies that we can hear. Now the speed of sound waves, if you remember from the last chapter, we talked about how the speed of sound waves on a stringed instrument was equal to the square root of the tensional force divided by the mass per unit length. If we now talk about the speed of sound through for wind instruments, or the speed of sound through different bulk materials, it's going to depend on something fairly similar. It's going to depend on Young's modulus, which is essentially what type of restoring force am I going to have, what type of tensional force I'm going to have, as well as the density of the material. Actually, I stand corrected. This is the bulk modulus for fluids and Young's modulus for solids, both of which depend on the density. Now, we know that for solids in general, there's going to be a much larger restoring forces than, say, liquids or gases, simply because of the nature of the material. What that really means is the speed of sound is going to be much greater in solids, as you can see here, than it is going to be in liquids, which is also going to be much faster than the speed of sound in gases. What this really means is, if we're underwater, sound is going to travel much faster than if we're simply in air, or if we looked at the propagation of sound waves through a solid versus a liquid. It's going to travel much faster through a solid than a liquid, much faster than through a gas. Much like in the last chapter, I talked about sound intensity being how much power reaches your ear divided by the area of the wave. In many cases, this is going to be a spherical wave, so the power is going to be divided by the surface area of a sphere, which is going to be 4 pi r squared. One thing to be very careful of here is intensity is always going to have units of watts per square meter. This should not be confused with sound intensity level, which is going to have units of decibels, and I'll talk about that in the next slide. One thing that is interesting is the intensity is going to depend on the square of the amplitude of the pressure wave, but in addition to the square of the frequency. So we can have the same intensity from different frequencies with different amplitudes. So it's kind of interesting to think about it in that way. So let's talk about this sound intensity level that I alluded to on the last slide. If we look at some various sounds here, the threshold of hearing all the way up to a military jet aircraft 30 meters away, and I look at this column over here that describes the intensity, the power divided by area, we can see that the threshold of hearing at the standard of 1000 hertz is 10 to the negative 12th watts per square meter. Military jet flying 30 meters away, happened very frequently when I was in Norfolk, is going to be 100 watts per square meter. We're looking at a range of 10 to the 16th watts per square meter. We're looking at a huge dynamic range here. It makes a lot more sense to define a sound intensity level by using a logarithmic scale, as you can see by this very, very, very important equation right here. So I'll put a star next to this guy. The sound intensity level is given by the symbol beta, and that's going to be equal to 10 dB. That's going to be a decibel, D-E-C-I-B-E-L, named after Alexander Graham Bell. It's going to be a tenth of a bell, or a decibel, multiplied by log of the intensity. This is going to be the intensity in watts per square meter, relative to some reference intensity, and what we use for that reference intensity is going to be 10 to the negative 12th watts per square meter. So for this chapter, you're seeing a log right here. You might want to brush up on your properties of logs. What this allows us to do is to look at a range of the same sounds going from up here to down there, and now we're looking at a much more manageable 0 to 140 decibels as opposed to the 10 to the 16th range that we're seeing on this side. So working in a log scale makes a lot more sense when we're talking about such a large dynamic range. I highly recommend that you look at examples 16.8 and 16.9 to brush up on some of the properties of logarithms. One word of caution whenever we're talking about sound intensity levels and intensities: suppose you have two sources. Each source might be putting out some intensity, so I'll have a intensity over there, and suppose I had another source over here that's putting out some intensity over here. I have a wave kind of coming like that. Here I am standing there with my backpack. I want to make sure that I add the intensities, and I don't want to add the sound intensity level. Sound intensity levels is going to be logarithmic, and you essentially cannot add them together very easily. You want to add together the intensity levels.